Okay, welcome back. Let me start this video by working some typical problems that you might see in your Achieve homework or on the written homework. And here's one real typical problem. You're asked to find the point or points on the graph of this cubic polynomial where the tangent line is horizontal. So let me just graph that cubic. If you went into Desmos or did this by hand, you're going to see something that looks like this. Right. And so the question says, where on this graph is the tangent line horizontal? Well, I can see here's a tangent line that's horizontal right here at this point, and there's one over here at these turning points. The tangent lines are horizontal. And so to find those points, I need to set the derivative equal to 0. Right? Because the derivative gives me the slope of the tangent line, and if it's horizontal, it has slope 0. So we can get the derivative function. Right? I'll find the derivative of this piece, subtract off the derivative of that piece, and so those linearity rules and the theorem that we saw allows us to differentiate these polynomials. The derivative of 12x, well, it's linear. 12x is linear, so its derivative is the slope. And subtract off the derivative of x cubed by that power rule is a 3x squared. So there's the derivative function. I want to know when is it equal to 0. Setting it equal to 0 and solving, well, we're going to get x equals plus or minus 2. And so I guess the points then, this point right here has x coordinate 2 and y coordinate f of 2, 16. So there's one point. And then the other point over here, x coordinate is negative 2, y coordinate is negative 16. Okay, so that's a real typical type problem. Another real typical type problem is you might be asked to graph the derivative function given the graph of f. Let's work one of those. All right, let me put up the graph of f here. And let's make f look like this. This is f of x. And we want to graph its derivative. So I like to do this right below. And to graph the derivative, I'm going to interpret it as the slope of the graph. And so the first thing I do is I look for, well, where's that slope equal to 0? Where do I have horizontal tangents? Those are easy enough to spot. Right here, there's a horizontal tangent. So at that point, the derivative is equal to 0. And here's another horizontal tangent. So at that point, the derivative is equal to 0. And then I just start to ask myself, well, what are the tangent lines doing? What are the slopes of the tangent lines doing? So if I just think about tangent lines, well, here's a positive slope tangent line, and it's still positive but getting smaller, getting smaller, getting smaller. Hit 0 here, and then these tangent lines go negative, 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 get more and more negative, still negative, but now starting to come back up to 0, hit 0, and then it goes positive. So I'm just going to sketch that in. I have positive sloped and coming down to 0, and then it goes negative, and then at some point it starts to come back up, and it hits 0 and goes positive. So I might have something that looks like this. So one thing I want to point out, and we'll see this again in a later section. One, okay, when the function has horizontal tangents, the derivative is equal to 0 there. When the function is increasing on an interval, the derivative is positive. Right? This function is increasing, increasing, increasing. The derivative is positive on that interval. And now, hey, the function is decreasing on this interval. And on that interval, the derivative is negative. And then the function starts increasing on this interval. And on that interval, again, we're seeing the derivative here is positive. Okay, so we'll come back to this in a later section, but he presents it in this section in the textbook. Let's move on. Okay, couple theorems. I'm not going to prove these. Maybe in your pre-calc class or algebra 2, maybe the instructor said, hey, we like, when we're dealing with exponential functions in calculus, we're going to want our base to be base e. Well, here's a reason why we like base e in calculus. The derivative of e to the x is e to the x. So the exponential function whose base e is its own derivative. Real easy to differentiate that exponential. Let me give you another theorem. If f is differentiable at x equals c, then f is continuous there. So differentiability implies continuity. If a function is differentiable at a point, it's continuous at that point. But the converse of that statement is not true. If a function is continuous at a point, it does not have to be differentiable there. And a nice counterexample here would be the function absolute value of x. Right? We showed in section 3.1 that function was not differentiable at 0. Right? We said if a function has a graph who's got a corner in it, then it's not differentiable there because the left-hand limit and the right-hand limit did not agree. So this function is not differentiable at x equals 0, but it is continuous there. The limit is equal to 0, the function value is equal to 0. So this theorem, differentiability implies continuity, but continuity does not imply differentiability. Okay, one more thing I want to just finish up with, and that is this. The graphical significance of a function being differentiable at a point. If a function y equal f of x is differentiable at x equal, what do I use here, a, then the graph of f is locally linear at x equal a. So what that means is this. You might have some function and it's curvy. Right? You might have something that looks like this, right? A lot of curves in it. This function is differentiable. And so at this point right here, even though the graph is bending, is curved, if I zoom in on this point, if I look at just like a little neighborhood around that point, the graph starts to look more and more like a straight line. It starts to resemble the tangent line there. So that's what it means to say that the graph is locally linear at that point. Zoom in on that, and you're going to see this. Go into Desmos, put in some polynomial, and then just keep zooming in, and zooming in. And what you're going to see is a straight line. So if a function is differentiable at a point, then the graph of that function at that point is locally linear. Now, that's not true for, again, this function here. We said the derivative of that function does not exist at 0. This graph is not locally linear here. If I graphed this in Desmos and I kept zooming in right here at x equals 0, it never looks like a straight line. It always looks like this corner. Okay? So a function is locally linear at any point where it's differentiable. Okay. I'm out of steam. I'm going to close up shop. I hope to see you all on Wednesday. Alrighty.